All right, so I was talking about how these nebula eventually collapse. Well, I didn't talk about that yet. All right, you have these nebula that have been around for a very, very long time. This is tremendous amounts of hydrogen and helium. We actually find these between the stars in our galaxy and in other galaxies as well. They pretty much they resist very well collapsing. Because of mostly thermal energy. If there happens to be a magnetic field around, that also tends to cause them to not want to collapse, and they also won't collapse because if they're spinning, if the gas and dust is also spinning. But let's say, for example, that a supernova takes place, and you have some region where there's one of these gas clouds, these giant interstellar clouds, which would, and by the way, they're many, many light years across. Okay, so stars are really very, very small compared to the size of these nebula. So if a supernova goes off, that tends to trigger these things collapsing, and so they begin to collapse gravitationally when as they heat up, they become what's called a protostar, and only when the core gets to be about 10 million Kelvin does fusion take place. Fusion is turning hydrogen into helium. And the star does that most of its life, right? That's basically what it's doing, is turning hydrogen into helium. And then as it dies, at the very end, it starts to fuse heavier and heavier elements. The more massive the star is, the heavier the elements it can fuse, all the way up to iron. Iron is the last straw. If it reaches element 26, this is a massive star that can fuse iron. But as soon as it does, the star collapses and it explodes in what's called a supernova. One of the greatest explosions, in the universe. And during that, the last part of the periodic table is created. Right, so that's what happens. Um, but by far and large, most stars that are maybe a few times the mass of the sun, or and in fact, the vast majority of stars are less massive than the sun. When we look at our own galaxy, most stars are less massive than the sun. Um, but of course, there's some stars that are much more massive than the sun, and the ones that are less massive tend to be the majority of stars, and they will eventually become white dwarfs. Right? They won't ever explode as a supernova. So white dwarfs will cool. It'll take billions upon billions, in some cases trillions of years for them to cool off, and then they'll just sit there as basically a giant carbon, um, this giant sphere of mostly carbon, because that's pretty much what these low mass stars fuse all the way up to carbon. I mean, maybe a few elements heavier than carbon, but not as much as mostly it just becomes carbon. Sometimes there's situations where there's binary stars. There's two stars orbiting each other, and then even low mass stars can explode as a nova, as what's called a nova. It's not a supernova. A supernova is much more intense, but these novas basically one star. Let's say the star has gone white dwarf, right? It's reached the white dwarf stage, but then the other star is close enough and you can take some of the matter falls off of not falls off, is gravitationally attracted to the white dwarf and falls onto the surface, and that hydrogen will explode on the surface over time, and that's called a nova. So this is actually a very famous supernova remnant. This is in the direction of this is in the constellation Taurus. In fact, it's gotten several designations. One designation, it's called the Crab Nebula. It's just because you look at it through a telescope, and it looks kind of like a crab. Although that you got to have quite an imagination. But one of the things that we know of the Crab Nebula, and by the way, it also is given the designation M1, Messier Object 1. Charles Messier was a French astronomer that was looking for comets about 200 years ago, and he cataloged about 110 different objects. Some of them turned out to be very, very incredible objects. Some are galaxies, some are like supernova remnants. Some are what are called globular clusters. There's all sorts of things. He didn't know what he was looking at. He just cataloged these things and said, "Hey, it's not a comet, so I'm going to catalog it and move on to another thing." But that was one of the first catalogs. Since then, of course, there have been lots of other catalogs. Anyhow, this one's called M1. We know that in the year what was it? 10? I think it was. I think it was in the year 1054. All right, so 1054 AD. Some Chinese astronomers wrote down that they observed a very, very bright light in the constellation. They basically observed a supernova in the constellation Taurus, and this is the remnant of that. This is hidden inside of this thing is a pulsar. That it is a rapidly rotating neutron star. But you go back to the year 1054. According to the Chinese observers, that this star was so bright that in the constellation Taurus that you could actually see it during the daytime, right? And at nighttime, it was so bright for a long, long time. Like I think it was more than 100 days. That at nighttime, you could actually read by the light of that. You could read by the light that was coming from this supernova. It was that bright. So that's like, the brightness of like the full moon. The source of energy in the sun and the stars is, of course, B, the thermonuclear reaction, the fusion of hydrogen into helium. All right, so this is just to give you a sense of, the size of planets. These are that's Neptune and Uranus, Saturn. This is kind of a scale, right there. There's the Earth, there's Mars. Notice, of course, the Earth and Venus are roughly the same size. Notice the Sun is much, much bigger. You could fit 109 Earths across the surface of the Sun, but the Sun is not at all the biggest star out there. I mean, there are some stars that are even bigger, right? Here's one called Vega, a very famous star in the constellation Lyra, a very bright star in the constellation Lyra. It's actually a summer. It's what I mean by that is if you go out at nighttime in the summertime and you look almost straight up, you'll see the brightest star you see is called Vega. So you look just straight up. But notice Vega is small compared to the red giant Arcturus, which is in which is what is that? It's more of a fall that's in Boötaz. That's the name of the constellation. It's in Boötaz. I always like saying that. Anyhow, this is an even bigger star called Alpha Ceti in the constellation Cetus, the whale. So remember, this is just to scale. And this is, even Alpha Ceti is small compared to Betelgeuse, right? And it's pronounced. It's actually technically called Betelgeuse, but since the movie came out, if you haven't seen the movie, you got to say his name 3 times and he appears. It's kind of a silly movie, but it's fun to watch. Anyhow. It's so since that movie, we all pronounce it Beetlejuice. All right, so Beetlejuice is even small compared to this one, C5a, which is a red hypergiant. All right, so just showing you there's lots of stars that are really, really much larger than the sun. Some much smaller than the sun. They're not showing you those here. All these stars lie within 300 light years of the Earth, which mean they're part of the Milky Way. The Milky Way, by the way, as we're going to see here, will extend 100,000 light years from one end to the other. All right, so now it kind of jumps to black holes. There is, of course, the neutron stars that are in between white dwarfs and black holes. Anyhow, it's the remains. If the remains of a supergiant star that has collapsed, so long after the supernova and material is flying off of this thing, if what remains is about 3 times the mass of the sun, then gravity basically wins. That's the ultimate win for gravity. And this thing collapses into a star whose is a dead star whose escape velocity reaches the speed of light. So that's the idea of. Why does the gravitation increase? So it's if you collapse, if you put them, it really has to do with the distribution of mass, right? If you take the same person on the same massive object, if you were to make such, this doesn't happen with planets, of course, but because gravity is an inverse square law, if you were to half the size of, in this case it would be a star, then the gravity goes up 4 times, right? So that they're just showing you that right here. All right. When a star collapses to 1/10 its size, the gravitation at the surface becomes, well, look, so it's going to be, if it's 1/10, then it's, 1/10 squared would be 100 times as much. All right, because of the inverse square law. When a giant star collapses to become a black hole, its gravity is increased. It increases at the surface. Yes. If the sun were to collapse and become a black hole, the orbit of the Earth would remain unchanged. Now, the other thing about that is the sun is never going to become a black hole. I know a lot of times you see this in textbooks, but the sun is just not massive enough when it dies to become a black hole. So that's never going to happen. But if it were, right, just using your imagination, the orbit of the Earth would not change at all. Right? So, all right, and then we get to the death of stars. Okay, so I'm going to categorize this. A dead star is when no fusion takes place, so long after the fusion has stopped. If the star has a mass of 1.4 times the mass of the sun, by the way, this is called the Chandrasekhar limit. This guy, this astrophysicist named Chandrasekhar, discovered this. He actually won the Nobel Prize for this. If the dead star's mass is less than 1.4 times the mass of the sun, it stabilizes into a white dwarf. What I mean by that is the inward force of gravity is matched by what? The Chandrasekhar was the one that proved that electrons will not be pushed any further. It's called electron degeneracy pressure. So that's what pushes back. All right, and then you get if the star has more than 1.4 times the mass, but less than 3 times the mass of the sun, then what pushes back is neutron degeneracy pressure. The neutrons, so this forms what's called a neutron star, also known as a pulsar. When they rotate, well, they're all rotating, but they call those pulsars. If more than 3 times the mass of the sun remains with this dead star, then that becomes a black hole. The escape speed becomes the speed of light, which is 3 times 10 to the 8th. And this equation right here tells us what